Zong.
Hello. Hi, Andre.
Hey.
Hi, can you hear me? Okay. How are you?
Good.
Oh, are you in the department? Or?
Yeah, sure. In 507. Can you see? Sorry, can you see?
Yeah, I saw the door.
That's 507.
Oh yeah, right. Okay. It really feels like a seminar. Okay, so I guess I'll share my screens so I can write. Okay, so. Should I wait for a few minutes or should I start?
Maybe it's best to wait because there's for some reason I put a wait room, which is a bad thing to do.
I see.
But because people arrive and then I have to admit them from the wait room.
Okay, yeah, no problem.
Yeah, let's wait a few seconds.
Okay, I'll just write the title.
Mm-hmm. Right, I think since I think everybody's here probably. I don't see any more people in the waiting room. So.
Okay, so maybe I'll get started.
Please start.
Okay. Yeah, so yeah, thanks for putting this series of seminars together, and I hope everyone's okay. Today I'll talk about the ongoing work with Bohan Fang, Melissa Liu, and Zheng Zong on the open Crepant transformation conjecture for toric Calabi-Yau 3-orbifolds. So I have talked about this, at least in this case, last semester in Melissa's seminar, but I didn't really explain how that works. Okay, so I'll try to make that clear today and move towards the general case where we try to have this result for all genus and also both open and closed Gromov-Witten invariants. Yeah, so okay, so let's start with some review of the basic setup. So I'll try to use this. Yeah, so also please stop me whenever you have questions or whenever anything's unclear, because I do realize that this screen sharing sometimes the video quality of the screen sharing is not that good. Yeah, so stop me if you can see and read anything. And yeah, I'm also trying to just test out this technology for teaching, and if you have any comments for that, that'd be also very helpful. Okay, so for the Crepant resolution conjecture or the Crepant transformation conjecture, our basic setup is a pair of K-equivalent manifolds or overfolds. So which I call X prime plus and minus. So the K equivalence just means that we have a diagram like this. So we have birational maps from some common space x0 to both x plus and x minus. So let's call these maps f plus and f minus, such that if I pull back the canonical bundles, they agree on top. Okay, so just in this setup, the conjecture, classical conjecture by Ruan, which is called the Crepant resolutional transformation conjecture, is that the quantum cohomologies of the two spaces. So here we take the Chen-Ruan orbifold quantum cohomology. So just the quantum cohomologies should agree. And this has been rephrased or reformulated in several different ways. And one of the ways that received most success is by Brian and Graeber in terms of Gromov-Witten theory. So there, in their formulation, the result is just that we should have an identification of genus 0 Gromov-Witten potentials. Oh, let me try to stick to my color scheme so that it's clear. Yeah, so we should have an identification of F0. So here, put a quotation mark for the equality, and some of you may guess why, because there are several things that go into this identification. So here, this equation, this equality sign means several things. So first, we need to have a linear isomorphism on just the cohomologies. And also we need to do a change in the moduli parameters. And last but not least, we usually need to perform some kind of analytic continuation. Continue. So usually these Gromov-Witten potentials are not some well-defined global object, and usually we need to use mirror symmetry to turn the picture into the B model picture, where we can hopefully have some nice analytic global object, and that's where analytic continuation comes into the picture. Yeah, so you can certainly generalize this proposal to higher genus. So in higher genus, we simply would like to identify the higher genus Gromov-Witten potentials. X minus. Yeah, so these higher genus potentials don't always make sense for all spaces. So in our project, we would like to focus on toric Calabi-Yau 3-orbifolds, where we have nicely defined invariants. And in fact, we would like to extend this to the context of open Gromov-Witten theory. So that's like the general goal. Okay, so I'd like to mention a last formalism of this conjecture, which is called, referred to as the Given-Tau formalism. So this is, I guess, down in the papers of Coates, Iritani, and Zong. Also a paper of Coates and Ruan, etc. So here we need to look at the so-called given tall symplectic space, which I call H curly H x plus minus. So this is just the usual Ruan cohomology, but we allow series in. So we look at Laurent series in Z minus 1. And here you can put some equivariant parameters. Yeah, so this space is a symplectic space. So it has a pairing given by taking residues, and I will not write down the explicit form. But inside this space, we have the so-called Lagrangian cone L, x plus minus. Or I guess more technically, they call this some formal germ of Lagrangian cone, but this cone it encodes. So it encodes information about F0. So for example, the J function would be a point in this cone. Yeah, whatever that means. So, so the Crepant transformation conjecture in this setting is just the statement that there exists linear isomorphism U from the symplectic space H of x minus to the H x plus. And this is required to preserve the Lagrangian cones. Okay, so that's that's some different formulations of the conjecture. So yeah, so obviously there have been a lot of works on this in different setups, and so this conjecture has come a sort of principle when you try to study the relationship between birational geometry and quantum cohomology. So today I would like to focus on just the toric case. So this case is particularly nice because we have a lot of tools at hand, and the birational geometry of toric varieties is also relatively well studied and described in terms of combinatorics. Especially, we have lots of nice results for in the mirror symmetry of toric varieties. So let me just start by mentioning one basic result, which is the toric. So I just call it the toric mirrors theorem. So this is, I guess, generalizing the result of classical result of Eventhal, but also mainly done by Coates, Forti, Iritani, and Zong. So the statement is that if X is a semi-projective toric orbifold, then the J function of X, J function of X is the same as the I function of X under the mirror map, which relates the Kähler parameters on the A side to the complex parameters on the B side. Yeah, so actually, in fact, the statement of so in fact, in CCIT, so the authored paper, what they actually showed is that both functions are points in the Lagrangian cone L of X inside the given tall space H of X. Yeah, so the I function is a very explicit hypergeometric function, and this statement allows us to just study the Gromov-Witten theory, or for our purposes, the Crepant transformation conjecture, just on the B side by comparing the I functions. And using this mirror theorem, I would mention, so they have, the Crepant transformation conjecture for the toric case, general toric case is known. And yeah, so as an example of previous work, I would just mention this paper by Coates, Iritani, and Zong. So this is CTC for toric case. Okay, so as before, we let x plus minus to be toric, semi-projected toric. I'll just always make this assumption. So toric overfolds related by a single wall crossing. In the secondary fan. So in this case, either x plus will be some partial resolution of x minus, or the two spaces will be related by a flop. So nice thing about the toric case is also that just k-equivalent toric, semi-projected toric overfolds are always related by different triangulations. So their cones are nicely related by different triangulations, and you can literally see the relation explicitly by the positions of the nav cones in the secondary fan. And we're just considering a basic case, so we just cross one wall, and in general, you can make a composition of these wall crossings to get from any face, so to get between any faces you like. Yeah, I'll try to talk a little bit more about this later, but in this setup, there exists a commutative diagram. Okay, so yeah, at the bottom, we have the map we want between the given Hell spaces. And also we have the equivariant K groups. And we also have the vertical arrows. So on the bottom, they have a map U, and on the top, we have the Fourier-Mukai transform. And the vertical arrows are given by the so-called gamma integral structure. Of Iritani. So the result is that we have map U, which is symplectic, and also linear in the equivariant parameters. Yeah, so everything here can be made equivariant with respect to the, some torus T, which makes the toric Crepant transformation x from x plus to x minus T equivariant. And this U also has a non-equivariant limit. But a very important thing is that after analytic continuation, U takes the I function of x minus to the I function of x plus. And yeah, and via the gamma integral structure, U is compatible with the Fourier-Mukai transform. So this is actually how they showed the U is symplectic, because the gamma integral structure preserves the K-theory pairing. So it respects the K-theory pairing and the just a symplectic pairing on the given whole spaces. And they have a version of this result for toric complete intersections as well. And yeah, I'll not talk about it here. Okay, so that's this. And let me talk a little bit more about the meaning of warp crossing in the toric case. So the picture is like this. So we have two cones, two neighboring cones in the secondary fan, so C plus, C minus, which share a common codimension 1 face, which is the wall W. So here, C plus minus are the extended nav cones of X plus minus in the secondary fan. Yeah, so we're zooming into some local place in the secondary fan. So this from just this picture with two top-dimensional cones and which share one-dimensional subcone, one-dimensional codimension 1 face, we can have a toric variety M and B. So this is the toric variety given by this fan. So this will be used as our B model complex moduli space. And so geometrically, this space is just so you can tell from this toric data that this space is actually just the total space of some vector bundle over an orbifold P1. So the P1 is given by the direction that crosses this wall. And each of the two cones will correspond to two charts, which I call M plus minus. So these are charts corresponding to the cone, top dimensional cone C plus minus. So they will look like a copy of C to some power K, where K is the rank of the space where the secondary fan lives in. And let's give coordinates, which is Q. Okay, I write Q plus minus 1 to Q plus minus K. So these are coordinates given by the toric data, but they will also serve as complex parameters. Yeah, complex parameters for our toric mirrored B model families, and they'll be mirrored to the Kähler parameters coming from the A model side.
Sorry, Zong, I missed the part about why is this some bundle over P1? This in where's that? I can see it's a toric variety, but why it's?
Yeah, so just because we have a map from, so if you take some vector, say some vector E, which is perpendicular to W, and then you can just project to the direction of E. So you can project to the direction of E, and the images of the cones will now become a complete monofan in a one-dimensional space, and so that gives.
Oh, so it's just this part. You think there's a fan of just this two.
Yeah, I just take these two cones.
Ah, okay, then okay, that makes sense. Okay.
Yeah, in general, you can consider the entire secondary fan or the entire secondary variety, but
no,
sometimes the
this
construction is
clarifies.
easier.
Yeah. Okay.
Yeah,
Just these 2 points.
Yeah. Thanks for pointing this out. Okay, yeah. So we'll just be focusing on the case of just a single wall crossing, and yes, and that's somehow makes things easier to study, I guess. Okay, so we have 2 charts, just the 2 charts given by corresponding to the 2 faces here, and inside these 2 charts we have 2 distinguished points, p plus minus, which are often called large radius limits, LRL points. Or rather here, it's actually some mixed type large complex structure point, the large complex structure limit point. So this is simply just the origin of these charts, which are given by letting all the coordinates k be 0.
Sorry, what do you mean by the mixed type?
Yeah, so in general, our spaces are not necessarily smooth here. So, I mean, for the large radius limit, we usually just mean the honest scalar parameters or
I see. Okay.
honest complex. But now you have some orbifold
twisted
parameters.
sectors from Chern and Ruan.
Yeah, exactly.
Yeah,
so that
But still, there is we have one space, and there's just one kind of Kähler class that we flow. Like one Kähler class is direction log P1, right? And one Kähler class that gets in.
Yeah, so that class will be most important, and that's so I guess the change of parameters here is just given by like q plus 1. If this is the parameter along the direction of the base p1, then this is q minus 1 to some minus some positive rational number, and the other q's will transform like q minus I times q minus 1 to some other power. So the direction, the parameter in the direction of the base is actually the wall crossing direction in this case. Let me draw a simple picture. So this is my base, orbifold P1, and I have like the 0 and infinity at the base, which are the large radius limit points. And in general, this entire B model moduli space will be some total space of a vector bounded over this. Oh, sorry. So this is MB. Okay, so what the work of Coates, Iritani, and Zong did in a general toric case is that they show that the I functions are locally analytic, at least in the base P1 direction in this modular space, and they found an explicit they picked an explicit paths from P plus to P minus to P plus, where they are able to compute their desired symplectic transformation U by some Bailey-Bars integral method. And so that's how they show that the U takes I minus to I plus. And then they compared this with the Fourier-Mackay transform by pulling back to all the toric fixed points and just computed their coefficients. And yeah, so that's how their work is done. Okay, so any further questions about this general setup? Okay, so I'll move on to discuss our goal. So as I said at the beginning, we want to generalize this framework.
So actually,
yeah.
Since you had this picture, would it be easier to prove that they both million bars are just solutions of some differential equation? Wouldn't it be easier to show the differential equations the same, or it's just easier to do the integral?
I think so. Yeah, indeed, there's a global differential equation or system on this space or some universal cover. I think I'm not sure that's easier to show. I mean, they gave a very explicit computation, like they gave all the coefficients of in a transformation U, and I'm not sure using differential system would be easier to show that. Yeah, I'm not sure. Yeah, but definitely in the background, this all fits in a global differential system. Yeah, okay. Does that answer the question?
Well, that was just curiosity. That wasn't a serious question.
Oh yeah. But definitely this global differential system is very important. Okay. Yeah, so as I said, our goal is to generalize all of this framework to be able to study higher genus Gromov-Witten invariants. And also we'd like to study open Gromov-Witten invariants. So our goal is the all-genus open-closed Crepant transmission conjecture, but we restrict our attention to toric Calabi-Yau 3-orbifolds, where we have a good access to both a B-model mirror for all genus invariants, but we also have nice definitions and understandings of the open Gromov-Witten invariants. So in our setup, we now focus on a toric Calabi-Yau 3-orbifold X. So in this case, the toric combinatorics is just very simple because the fan of X is given by the cone of a regular triangulation of a polygon or a lattice polygon. So for example, so I had a couple examples in my last talk, but for example, C3 is, so the cone of C3, sorry, the fan of C3 will be the cone over just the simple triangle, where this is 1, 0, and this is 0, 1, and 0, 0. So yeah, the fan is just a single smooth three-dimensional cone. And as another example, the KP2, which is the total space of the canonical bundle of P2, the fan is the cone over this triangle. Yes, so is of this, I should say, triangulated triangle. So here this point is 3, -1, and here this is 0, 1, 0, 0. And in the middle we have 1, 0. Yeah, so there will be 3 top dimensional cones, and if you just look at this picture, this should be reminiscent of the cone for the surface P2, but we're like taking the canonical bundle, so it's like putting this surface at some hyperplane in a 3-dimensional space. Okay, so based on the same polygon, we have another triangulation which just removes the subdivision. So we'll just have a single cone, but now this cone is singular, so this will give the fan for the toric orbifold, which is C3 modulo Z3. And this arrow which is subdividing the triangle in the middle lattice point, gives a Crepant resolution from KP2 to C3 modulo Z3. Yeah, so in general, if you look at a pair of toric Calabi-Yau 3-orbifolds different by wall crossing, then either it's given by a star subdivision at some lattice point given in this example, or you can have the two spaces are related by a flop. In which case you would pick a common quadrilateral and just simply switch the diagonal. So this is a simple example for a flop. Okay. And yeah, so for a toric Calabi-Yau 3-orbifold X, we can have open Gromov-Witten invariants. So these are packaged into oh, sorry, my screen is frozen. Let me fix that. Try to open it again. Okay. So this can be packaged into generating functions fgn of x lf. So here, so L here is a Lagrangian suborbifolding X, which is called the Aganajich. Sorry, Buffer ring. Yeah, so it's a Lagrangian suborbifold. Yeah, I tried to talk about this last time. So it is so this is a real three-dimensional orbifold, which is the union of orbits of a smaller real torus action on X, and it has a pretty nice properties because it, for example, intersects a unique torus invariant curve in X, and that also makes it easier to study just combinatorially. So this will be the boundary condition of our open invariants. And we also have additional data, which is an integer f called the framing of the brane. Okay, and the G, so in a subscript, the G is the genus of the domain curve. And N is the number of boundary components. Oh, boundary. Yeah, so I guess a generic picture of, so these open Gromov-Witten will account for stable maps from Riemann surfaces with boundaries into the pair XL. So a generic picture of a map will look like this. So here I have a surface of genus 2 with 3 boundary components mapping to the pair XL. So this will be roughly accounted for by the open invariant F23. So in this case, yeah, I will not give the precise definition in this case, but it's
question is L has just one component or can have several components?
It's just one component, but it can have non-trivial generic stabilizers.
Okay.
So it can actually be an orbifold. Okay. Oh, sorry, not even orbifold, but yeah, anyways.
Can you say what L is in the examples above? Like KP2 and...
Oh, okay, so for KP2, so L, you can have several different choices of L. Okay, so let's do the KP2 example. Yeah, so KP2, I guess easiest way is that, so on KP2 you have a 3-dimensional torus action. So it's a 3-dimensional torus, but inside here you can take a two-dimensional and real subtorus. So this is called the Calabi-Yau torus. So it's just the torus so we're just taking out the factor that acts trivially on the fiber direction of the canonical bundle. And so now you can look at I guess you can look at the moment map for this two-dimensional real subtorus. And so, okay, so let's see. So the image of that, yeah, how should I say this? So, yeah, so the image of the torus invariant curves under this two-dimensional moment map will look like the dual of the fan that I drew. So so this is a fan, but the image of that will be the dual under the dual planar graph, which is the toric graph. So this is just a dual plane graph. And then the Agnaja-Schwafa brane. Oh, I'm not sure why this is happening again. Yeah, so the Agnaja-Schwafa brane would just lie on the preimage of a single point in some line segment here. So it will be defined by a set of equations. So just adding, so you take, when you construct the toric variety as a symplectic quotient, you just add on a few more equations to cut down, and that will cut down dimensions furthermore until you get real three-dimensional space. But the point is that the brane is invariant under this T prime R, this smaller real torus action. And okay, and I guess topologically you have this L is isomorphic. Yeah, be isomorphic to let's see. So it'd be isomorphic to S1 cross R squared, but modulo some, possibly modulo some finite group action because we can have non-trivial generic solid stabilizer. Yeah, yeah, sorry, I'm not writing down the exact formula, but I'm just trying to give a general flavor. Yeah, so you can pick the brane to be any position in X, so you can make it to intersect any torus invariant curve you have. So you can like have a brane here or have a brane here. So you have different choices.
But I was asking earlier, why can't you have several of them at the same time? Is that the course that this theory doesn't work this way?
Yeah, I guess. Yeah, I guess for the theory we'd look at just one of them, and that's so also the early physics predictions are just focusing on one brane, I guess. I'm not sure what the theory look like if you have multiple boundary components.
Yes, we can have more than one L, but right now let's just in this talk just do one L.
Okay, yeah, I guess. Yeah, yeah, I think you might just, yeah, I think in general it's more complicated, and you might have to account for subtleties of the open parameters corresponding to different branes. Okay. Okay, yeah, so that's my vague introduction to open Gromov-Witten invariants. But the point of this project is to study these invariants from the point of view of mirror symmetry, and we're actually one of the main motivation for studying toric Calabi-Yau 3-orbifolds is that it has several different nice families of mirror B models. So I mentioned 3 of them. So the first one is, I'm not sure why this is happening. So the first one is a pretty well-known Hori-Vafa mirror. So this one is a family of also Calabi-Yau 3-folds, which, so it's given by XQ is the hypersurface H, X, Y, Q equals to UV inside C squared times C star squared. So here, UV are coordinates here in C2 and XY are coordinates in C star. And this H is a polynomial depending on the toric data of X. Or I guess, yeah. Yeah, so as I said, this is a Calabi-Yau, sorry, a Calabi-Yau 3-fold. So in this case, the mirror symmetry is manifested in the fact that the period integrals of the non-vanishing volume form omega q on xq, omega q check on xq check. So this gives you the components of the I function of the A model X. And so this family of this construction is actually pretty general. You don't need to have a Calabi-Yau 3-fold to start with, but it works for any dimension. So another pretty general construction is the Landau-Ginzburg model. Yeah, so here you have a superpotential on just three-dimensional torus. Okay, I'm writing T prime. So T prime is the Calabi-Yau torus that I mentioned before when we talk about Ginzburg rings. So this superpotential has form H, X, Y, Q times Z minus U1 log X minus U2 log Y. Okay, so yeah, so the X, Y, Z are parameters or coordinates on C star Q, and here U1, U2 are equivariant parameters. Of the Calabi-Yau 2 torus. So this is two-dimensional Calabi-Yau torus. So in this setup, the mirror symmetry is okay. It's seen in the an isomorphism of Frobenius structures. So on the A model side, we have the quantum cohomology of X, let's say T prime equivariant. And so this comes with a product, which is a small quantum product, and also the orbifold equivariant orbifold Poincare pairing. And on the B model side, we have the Jacobian ring of this superpotential with the usual product and the residue pairing. So so this isomorphism is actually an isomorphism of Frobenius structures. And I think these two are both semi-simple Frobenius manifolds. So you can have good canonical coordinates on the two sides. Yeah, so these two families are sort of general constructions. But for toric Calabi-Yau 3-folds, we have a particular nice third family of B models, which we would like to focus on. So this is mirror curves. So, okay, so this is a family of affine curves, CQ, which is, so it's a hypersurface in C star 2 defined by the equation H, X, Y, Q is 0. Yes, so I should say, so these H's are the same in all the three families. So the H is given by the toric data, and I'll write down the example. Actually, just right now. So that in the example of KP2, so H is given by, yeah, so recall that the fan of KP2 is given by the cone of this triangulated triangle. Yeah, I'm still trying to learn how to draw straight lines. Okay, so we have 4 lattice points in this triangulated polygon, and each lattice point will correspond to a monomial in H. So in this case, H is given by the formula x plus y plus 1 plus qx cubed y minus 1. Yeah, so this x is given, so this first term x will correspond to this middle point, which has coordinate 1, 0. So this is x, and y is put here, which has, so the powers of x and y are the coordinates of the lattice points. So y corresponds to this coordinate, so this is 1, 0, and this y corresponds to 0, 1. And the third term 1 will correspond to this origin. And finally, the last point will correspond to this lattice point sitting at 3, minus 1, but now there's a complex parameter q in front. Okay, so as I said earlier, the dual toric graph of this triangulation is like this. So the mirror curve, at least topologically, it will look like a flattened version of the toric graph. So the mirror curve in this case is given, it can be drawn like this. Yeah, so each infinite leg of the toric graph will correspond to a puncture on this affine curve. And then you see there's a triangle in the middle, and that gives us a like a hole in the middle of the mirror curve. Yeah, so if I take an Agnacich-Rafa ring L, so on X it will intersect a unique torus invariant line which corresponds to a 2 cone in the fan. So maybe I put L here. And as I said earlier, the image of L under the moment map will be a single point on the toric graph. Yeah, so this is the toric graph. And this is the fan. So, but in the picture of mirror curve, it will correspond to a puncture on the mirror curve. So the puncture corresponding to this leg. But in general, the Agnacich-Rafa ring can have non-trivial generic stabilizers, so it will correspond to a series of punctures corresponding to this leg, and that's more complications in the overfold case. Okay, so this mirror curve CQ will be a Riemann surface of genus G. I put a dash on it to distinguish this from the genus G coming from the Gromov-Witten theory. And this genus is equal to the number of interior lattice points of the polygon delta. So this delta is just this triangle on the outside. And we can have a compactification, a compactified mirror curve, which I just call CQ bar, which is the compactified. So this is a compact Riemann surface, and you can compactify this actually in a family of toric surfaces, compact toric surfaces. So this compactified mirror curve also has genus G dash. Okay. And also a very important thing is that we have of one form. Maybe let me not write cross pages. So we have one form which I call phi. This is log y of dx over x. So this x and y are coordinates on the ambient space C star 2. So this is the Liouville form. So the reason, so this new B model family is actually related to the previous two that I mentioned in the following sense. So we have a form phi on this mirror curve CQ, and the period integrals of along one cycles of this phi can be identified to the period integrals of this omega check Q on the Horry-Witten mirror. So in this sense of integrals, these two, the theory on the Horry-Witten mirror can be reduced to the theory on the mirror curve. And also for the mirror curve, you can have so the following function, which is the piece, which is u1 log x minus u2 log y. And so this can be viewed as, so let's call this x check. So this can be viewed as a superpotential on a mirror curve. So for this, you can also view the mirror curve as a Landau-Ginzburg model. And it turns out that this Landau-Ginzburg model will be equivalent to the bigger one that I mentioned above. So you can extend this isomorphism for Frobenius algebras to the mirror curve, and you can also identify the oscillator integrals of the two superpotentials. And yeah, and this is all described in the paper by Bohan, Fang, Melissa, and Zong. So this is the process called dimensional reduction. So the upshot is that you can reduce all the B model theories to the simple one-dimensional B model family, which is the mirror curves. Okay, so this family will be what we to work with in our setup of the Crepant transformation conjecture. So let me just describe how it works in a disk case. So for disk, we're looking at F01. So you have a genus zero component, genus zero domain with only one boundary component. Yeah, so the mirror curve will give us more powerful mirror symmetry results. So in a disk case, all we need is the disk mirror theorem. So this is first conjecture in physics by Aganagic, Vafa, and also Aganagic, Klein, Vafa, and proved first in the case of KP2 by Graeber and Zaslow, and then in the general smooth case by Fang and Liu, and also in toric general orbifold case by Fang, Liu, and Zong. So simply speaking, this is just saying that F01 of x, so the generating function for the disk invariance of xl is equal to an integral of the Liouville form on the mirror curve along some path. Okay, so the path, so the path is is okay. Let me draw again the toric graph and the mirror curve. So recall that, let's say we take a Untitled brain on this leg of the toric graph, and it will correspond to a puncture here on the mirror curve, and the path is just a path based at this puncture to a neighboring point x, which will be the open moduli parameter. So this you can view as, so this integral you can view as some sort of Abel map on the compactified mirror curve CQ, where we fill in this puncture. So you based at this puncture. So this is just saying that under an open closed mirror map, you can recover the disk potential of the A model just by an integral on the B model. Yeah, and there's some complications where your brain L can be non-effective, or meaning that it can have non-trivial generic stabilizers, and on the mirror curve you correspond to several punctures, but then you can manipulate integrals and add coefficients to. So in that case, the disk potential will be a linear combination of the integrals with coefficients given by roots of unities, and so that's the general result. Okay, so
you mean the disk function will be a sum of this integrals over paths from this several points to a given point?
Yeah, so in that case, the generating function f will not be a single value function, but it will lie in it will take value in the cohomology of some b mu m. So m is the So you also have m components, and on the right hand side we have like m integrals. Yes. So but then there's a linear combination matrix involved, so it's not component wise equal, but like one of them will be the sum of all of the integrals, but then for the others you need to take different coefficients. Yeah. Okay, so just using this, and we can just using this we can do the disk Crepant transformation conjecture based on the observation that we can have a global family of global defined mirror curve. So global. Sorry, not writing well. Global mirror curve. And here by global, I mean defined over RB model moduli space MB. Yeah, so here our setup is we now have a pair of toric Calabi-Yau 3-orbifolds. Which differ by a single wall crossing. And we have corresponding boundary component conditions. So corresponding framed Untitled brings. So this corresponding just means that, for example, if x plus is partial resolution of x minus, then L plus should be in the preimage of L minus. But there it can't. So there are again more complications. So say the partial resolution can resolve singularities along L minus. So you have multiple components popping out, and you need to take into account of those open Gromov-Witten invariants with boundary in the different components sort of carefully. And I'll not going too much into that complication. So in this setup, we have the following result, which is that we can identify the mirror curve equations. So H plus will be some monomial times H minus. Of course, you need to have a relation between the coefficients, but this implies that, so this implies that the mirror curve, or generically speaking, the mirror curves for the two faces x plus minus will be isomorphic. Just because you can identify the defining equation in C star 2. So this implies that we have a family of mirror curves over the B model moduli space MB. So let me do this, illustrate this in an example of KP2. Yeah, so the example of KP2 resolving C3 modulo Z3. Okay, so we said earlier that the mirror curve for KP2 is x plus, okay, y plus 1 plus q plus x plus 3, y plus minus 1. And the mirror curve for the orbifold is that, so again, you would look at the toric data and you can write down just the equation just based on toric data. And the result is that you have q minus x minus plus y minus plus 1 plus x minus the third and y minus the negative 1. So you see that the exponents of x and y match up term-wise. So the proposition just saying that you can match these two equations term by term after doing the change of parameters. Q plus is equal to q minus to the negative 3, and x plus is q minus times x minus. So okay, so you need at least need to match up these two terms. And also y plus is y minus. So in this case, actually the secondary fan is just, so the secondary fan looks like just a complete fan, one-dimensional fan, but so the plus face will be a smooth face, but then the orbifold face has singularities. And your secondary, so the B model moduli space would just be the secondary variety, which is a weighted projectile line P13. And this relation between the Q is just by the change of coordinates on the two charts of this projectile line. Yeah, so let me draw this picture. So this on the base, we have MB. And we have 2 points, P plus and P minus, corresponding to the two faces. And for generic points in a moduli space, our mirror curve, our compactified mirror curve would just be elliptic curve. So it has genus 1. And so, okay, so above this P minus, the curve will also look the same. But above P plus, the curve would degenerate into a nodal curve, a rational nodal curve. So this genus will degenerate into 3 nodes, like this. And if, let's say, if you take L minus to be the Alganacci buffer brane corresponding to this puncture, then on the plus side, you correspond to this puncture. So, okay, so pictorially, you can see this correspondence. Yeah, so you can construct this global family of mirror curves for any pair of wall crossings for a toric Calabi-Yau 3-orbifolds. And that's somehow the single most important construction in this picture. Yeah, again, so the big thing is that we want to have global objects on the B model side.
Question.
Yeah.
If I have this curve, so I have like curve and some toric surface, and
right,
and it hits the toric divisor at some finitely many points, and so then I kind of pick one point where my brain sit,
Yes.
Then in general, in some family, that point, you know, that's kind of branched family. We have like monodromy, right? I mean, is that,
Yeah, yeah,
is it,
exactly. Yeah, yeah.
but that's so in principle.
Oh, I can't hear anymore.
Sorry, I have to press the unmute button. So if I
okay.
have, is there some? I thought there's some like a monodromy, meaning if I have like a choice of a marked point in one corner of your moduli space, is it really uniquely gives you a marked point on the other, or it's just or in principle it depends on the path?
So a situation that can happen is that, okay, so if you have in a simple case like this, where you have just one mark point corresponding to
in this case, we just have one mark point and one infinity.
Yeah, but if say the bring on the minus side is singular, and you can have say two mark points, and it will correspond to two other mark points on the plus side, but then in some middle of the modular space where say the curve is degenerate, then the two mark points can collide. So monodromy around that point will allow it to switch the two mark points. So that's the monodromy you see.
Okay, thanks. Yeah, but that exists. Monodromy exists.
Yeah, and it's very important.
Okay.
Yeah, that's a nice observation.
So is this related with like some monodromy analytic continuation of like Milton-Barnes analytic continuation?
Yeah, exactly. So what will happen is that okay, so there's some mysterious point in this modular space called the conifold point. So where your differential system can be singular, or I don't know what's the exact word for that. But then, yeah, you need to carefully choose your monodromy around that point. So picking different monodromies will reflect in the Milton-Barnes integral by you need to take different residues. So your subdivision of the residue or your partition of the residues for the two sides will be different. So depending on what you exactly want to prove, you want to pick the correct number of times that you turn around this point. And that's actually a very important thing in in Coates Iritani-Zhang's paper, using the Milton-Barnes integral to show that I functions can be analytically continued. Yeah, so in this case, actually the mirror curve above this point will be a singular mirror curve, or a degenerate mirror curve. So it's also a nodal curve, but with a single node, self-intersecting node here. But I'm not sure about the relation in the general case between the conifold point and like the degeneracy locus of the mirror curve. Yeah. Okay, so based on this global construction, we have several observations. So it's just first of all, this Liouville form phi is also global, just because it's restriction of an ambient form onto the mirror curve. And then also, as we said, the vaguely corresponding branes will relate to corresponding punctures. So we can also sort of analytically continue the path we need to take for the path integral to get the disk amplitudes. So just based on these simple observations, we're able to get the disk CTC. So the statement would just look like, so on the plus side, you have F01 plus, and we said this is roughly equal to the modulo some technical details. So roughly equal to the path integral of the Liouville form on the plus side. But then you can analytically continue this integral to an integral on the minus side. And that by the mirror theorem for this again is equal to the this potential on the minus side. So in this sense, we establish the equivalence or the equality between the dispotentials on the two sides. And here, in this process, you need change of parameters and you need change of parameters and analytic continuation. And as I said, the process can be more complicated when the branes are singular, and but we can manage how to match up the different components exactly. So that's not quite a big problem. And yeah, and this result generalizes previous results by Ke and Zhou. So their work is on the case where the brane is outer and effective, meaning that the brane intersects a non-compact torus invariant curve, and also the brane is smooth itself. And also in the AN case by Brini, Cavalieri, and Ross. So this is the case with AN singularities. Okay. Any questions for this? So I'd like to, in the remaining time, I'd like to discuss our ongoing work in the general case. So as I said earlier, we want to generalize this framework to higher genus and also open close invariants. So there's a work in this direction by Coates and Iritani. Just for the Crepant resolution KP2 to the overfold C3 modulo Z3, and they formulated this. Okay, they formulated this problem in terms of Fock sheaves, which seems very complicated. The paper is over 100 pages long, and and they also showed that the generating functions for Gromov-Witten Fg are modular. So the point of our work is to use the B-model mirror curve to provide a simpler, much simpler framework to study this kind of problem. But for this, we need to use also upgrade our use an upgraded version of the mirror symmetry for the open Gromov-Witten invariants. And in this case, what we need to use is the so-called remodeling conjecture. So this is proposed first by Bouchard, Klein, Marino, and Paschetti. So hence the name BKMP, but it's proven in the smooth case by Einar Orrington. And in the general case by Fang, Melissa, and Zong. So this is an all-genus open-closed mirror symmetry statement for toric Calabi-Yau 3-orbifolds. So the statement has, let me write down the statements in multiple components. So first of all, one thing is it subsumes that this mirror theorem, so which is F01 is, okay, roughly speaking, integral of the Liouville form. And also annulus. So here G is 0, but we have an additional boundary component, and it's 2. In this case, F02 is roughly the same as minus integral of a 2 form, which is called the Bergman kernel. Okay, I'll talk about this a bit more later. And in general case, if 2g minus n plus 2g minus 2 plus n is positive, so this is like the stable case. So in general, FGN is roughly the same as some sign factors times the integral of n form, omega gn. So this will be invariance coming from the Einard-Orrington topological recursion. Okay, and also lastly, we have a statement for the closed sector. So in the case G is greater than 1, we have the usual closed Gromov-Witten potential, or the general function for Gromov-Witten invariance Fg is equal to, again, some signs times omega G0. So this is some function also can be defined by this topological recursion process. And for G0 and 1, we need some special care. So for G0, we need some special geometry properties of the mirror curve. And for G1, we need some, I guess, a quantization formula of given tau. So the statement would be look a little bit different from this. So let me, philosophically, this just means that the A model Gromov-Witten invariance can be captured by integrals by invariants coming from the B model mirror curve. And these invariants are given by the Einard-Orrington topological recursion. Let me now explain what is this recursion process. So EO topological recursion. So the input is very simple. So for the input data, we need the compactified mirror curve CQ, which they call a spectral curve. It's just a Riemann surface, and also the Liouville form phi from before. And lastly, we need additional piece of data called the Bergman kernel. So this is a new piece of data. This is a symmetric, meromorphic symmetric two-form on the twofold product of the mirror curve. So this is a symmetric two-form, and it has the following properties. So if we're given a symplectic basis, so A1 to AG, so G is the genus of the compactified mirror curve, and B1 to BG. So just a symplectic basis of the first homology group. We can find a unique Bergman kernel, or also called the fundamental differential of the second kind. So unique B such that, so first of all, B has, let me say the only poles along B, only poles of B is a double pole along the diagonal in the twofold product of the mirror curve. So locally, B would look like, so locally B of Z1, Z2, if these are local coordinates around some point in the diagonal, so this will look like Z1 minus Z2 squared plus some holomorphic parts. And also another important thing is that B is normalized by the acycles. So by the elements A1, AG we choose, in the sense that if you integrate, let me stick to my color choice. So if you integrate B. So if you integrate one point along any of the cycles of BP, so this integral will give you a one form, but the requirement is that this one form is 0 for any choice of A cycle, any of the GA cycles you pick. So given this A cycles, you have a uniquely determined Bergman kernel. And if we switch from a symplectic basis AB to some other basis A prime B prime under a symplectic transformation, like say some matrix n from some matrix n, then we can compute the change in the Bergman kernel B prime explicitly from the original Bergman kernel and this transformation matrix. Okay, so that's the input data. And just from this input data, the topological recursion process will produce the forms omega GNs. And this is a meromorphic symmetric n form on the n-fold product of the mirror curve. So you will start by taking omega 01 to be 0 and omega 02 to just be the Bergman kernel. And in general, the higher omegas, say omega Gn, will be obtained by recursive formula from either with lower G or with lower N. And so this construction only depends on the choice of your Liouville form phi and the choice of Bergman kernel B. And in fact, there's a graph sum formula so I'm not writing down the general definition because of time, but you can see the dependence of later omega GNs on the Bergman kernel very explicitly from this graph sum formula. So you take a set of decorated graphs corresponding to Gn, and for each graph you assign a weight. Yeah, so this formula is by Dunning. Okay, I just write the initials by Dunning, Barkowski, Orenton, Shadring, and Spitz. Oh, DOSS. So the upshot is that this recursion process only depends on the choice of the Bergman kernel. I mean, once we fix the Liouville form phi, and in turn, this Bergman kernel all depends on their choice of normalizing A cycles and also the B cycles. And also these just recall that these topological recursion invariants, if we take appropriate integrals along combinations of paths on the mirror curve, then we can relate them back to the A model Gromov-Witten invariants. And that's the meaning of this powerful statement, which is the remodeling conjecture. Okay, since I'm running out of time, I'll just say in 1 minute how our strategy for the general case works. Strategy, I can't spell it. Strategy for general OCT, general CT, let's say it's CTC. Oh, I should say that, yeah, so after you define all the omega GNs for positive, and you can also define the so-called free energy, which will give us the usual FGs, so in a closed sector. Okay, so our strategies. So in general, recall that we have our construction earlier in this case gives us a global mirror curve over the B model moduli. And also we have a global Liouville form phi. So this phi is global. So what we really need is understand the analytic continuation of the Bergman kernel. Understand analytic continuation of B. Because the entire topological recursion data is now based on this Bergman kernel. So the picture is that we have this B moduli and B, and we have two distinguished points, P minus and P plus. So locally, we have near P minus, we have a choice of A and B cycles, which give us the Bergman kernel B minus. And locally near P plus, we have also choice of A, B cycles, which are symplectic base, which is again a symplectic basis of H1 of the mirror curve. And this gives us the Bergman kernel B plus. Okay, so if we understand how B minus can be analytically continued, so if you understand the analytic continuation, I mean the relation between the analytic continuation of B minus to B plus, then we're basically done. But here, this boils down to understanding how the A and B cycles analytically continue. So on this global family of mirror curves, we have a Gauss-Manning connection coming from just the local system of H1 of the compactified mirror curve. And then we can, let me write down like this way. So we can just parallel transport the sections A minus and B minus to the plus side. So around P plus, we have a different symplectic basis for the mirror curve. And the two bases differ by some symplectic matrix M. And then, so this data tells us that, tells us how the analytic continuation of the beta minus, of the B minus work. And then, so this B minus will be determined by a different set of different symplectic bases. And once we know the matrix M, then as I said before, we can explicitly write down the relationship between B plus and B minus, which then give us the relationship between all the topological recursion invariants omega Gn. So so the point is that M give us how to get B plus in terms of B minus. And then this tells us how omega Gn plus depends on omega Gn minus. And by the remodeling conjecture, we can now determine how the open invariance depends. Yeah, so that's the general strategy. And currently what we're working on is to explicitly compute this matrix M. And our basic strategy is that we can relate M. So because from properties of the mirror curve, we can relate M. We can choose nice AB cycles just based on the components of the I function. And we can we're hopefully using the explicit paths of codes Iritani and Zong, which gives us the explicit expression of how the I functions relate, and that we're trying to extract this matrix M explicitly from the relation of the I functions. And yeah, once we have this M, we can just apply this general process of changing the Bergman kernel, and that will imply the Crepant transformation conjecture. Yeah, sorry, I'm running over time, but yeah, that's all I have today. Thank you.
Not sure, how do we applaud over Zoom? I don't know. Maybe we should. Clap, clap. Yeah, says Henry. Yeah. So thanks, Zong. That was great. How about questions?
Yeah, questions.
I had a technical question. Do you mind we post your note on the website or?
Oh yeah, it's fine. Yeah, sure.
Yeah, send me the website. Send me the note. I just put on the seminar website.
Okay.
And,
yeah, I'll do that.
And then we'll figure out. Maybe we can So Columbia seems to be running out of space in terms of storing video information. But
Oh, really?
yeah, we can probably store you. We can definitely put you up on YouTube if you want. But we'll find out.
Oh, okay.
Well, we'll discuss
Can we
this later.
at least-
No, I think notes
yeah.
this is uncontroversial.
Okay.
So, how about math questions?
Yeah, sorry, I'm rushing a little bit through the latter part.
No, it was great. I think it's
Hopefully it
supposed to be. I think the idea of the seminar is supposed to be start slow.
Okay.
So okay, so maybe then a couple of announcements. One is, as we discussed before, we have to. Hopefully, we can schedule everybody to speak, and the person who kind of agreed to be in charge of schedule is Henry. So please be in touch with him so then work out some order in which is convenient for you. And then and the second that like an encore of my course starts Wednesday, I think 10:30 New York time. So that's there'll be.
Andre, you're muted. We can't hear you. Andre, we can't hear.
Yeah, we can hear.
Oh, I don't know. From which point on? Yeah. So yeah. So I was gonna say that there's some kind of like a second edition of the course will start Wednesday, but this will be more about elliptic theory. So I guess we'll redo if you learned K theory, now you're gonna learn elliptic homology, hopefully. And then I'll send the actual info in the channel, which is now what I will say. Don't be surprised. The channel's been renamed. It's now, since that course is over, I renamed the channel to be just a Telegram channel for the seminar. Okay. Other announcements? All right. Next, in 1 week we have Konstantin. And then we'll see. All right.
I have a question.
I can clap here. So. All right. Thanks, Angi, one more time.
Oh yeah, thanks for
Yeah,
putting
thank you.
together
That
the
was
seminar.
great.
Yeah.
Thank you.